Welcome back to your PN39 Part B notes, where we're going to finish our discussion about the basic fundamentals of vectors. Okay, so previously we learned, at the top here it says, we learned how to calculate the magnitude of a vector given its components. Now again, every time you hear this word components, know that we're talking about this, when it's in this form, where you have the horizontal and the vertical movement of that vector to give it that length and that direction. Recall again, vectors consist of both magnitude and direction. We focused on magnitude. We used Pythagorean theorem or the distance formula to find that magnitude. Now we're going to focus on that direction. Now, I do want to say that we call that direction a direction angle. Very nice, right? And the angle, we use the word, the Greek letter theta, so the angle theta that vector v makes with the positive x-axis. This is so important right here. So what that means is that if you have an xy axis and you have, let's say, a vector over here, the direction angle comes from the x positive axis, kind of like the unit circle, and rotates counterclockwise to get there. Now, that is what we call the dA, which is the direction angle. I a lot of times say directional angle because that's kind of just what I say. Anyway, so I do want to say again, the direction angle is just like the unit circle, rotation from the positive 0 degrees, if you want to think of it that way, all the way around to where you're ending with your vector. Now, it says, if given down here, it says, if given the magnitude, notice the notation, magnitude of vector v, and the direction angle, theta, we can work in reverse direction to find the component vector. And remember, the component vector is this thing. Okay? So, if you're given the magnitude and direction, you can then find the component vector or vice versa. So I just want to come down here, and this is really, really powerful. What we're going to be talking about right here, this right here, very, very powerful. It says, if v has direction angle theta, the components of v can be computed using the following formula. And what it's saying is you have the magnitude of v cosine theta, magnitude of v sine theta, and this is going to give you that component vector. And if we want to talk about the horizontal and the vertical moment, we'll call it x and y. Now, this is not magic. This formula, it is a formula. If you really, really want to think about this, this is not magic. We can just talk about it super fast, where figuring out where it's derived from. If you create a vector, let's say in the first quadrant, and I change the colors here, bring this down to create a nice little right triangle. Notice that when I bring that length down, it always comes down to the x-axis, just like we did in the trig unit earlier. We know this is the movement on the x. We know this is movement on the y. This is some angle theta, so we're just going to put theta there. And we know that when we find the magnitude, we end up, we're just going to call it this right here. Now, I can use the trigonometry that we've done before, SOHCAHTOA, so we can say cosine of the angle theta is equal to the adjacent side, which is x, over magnitude of v. And if I wanted to solve for x by cross-multiplying, putting this over one and cross-multiplying, or multiply both sides by magnitude v, you'll end up with x equals the magnitude v cosine theta. Notice that is this right here. That's that x component. So if I switch around and switch to green here, I'm going to now prove how this comes about. I can just go sine of the angle theta is equal to the opposite side, which is y, over the hypotenuse, which is the magnitude, and cross multiply or multiply both sides by magnitude v to solve for y, and you end up with y equals sine, boop, 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 boop. I forgot, I was like thinking about something different, sorry you guys. Doop, doop, doop. Magnitude v sine theta. And that is that right there. So, not magic here. It is a formula, but it is just stemmed from right triangle trigonometry. Okay, so let's see how this actually works. So it says find the components, the component vector, this right here, with a direction angle of 115, by the way, it should say degrees here, and a magnitude of 6. So, and I do want to say that many, many times, you know, when we talk about airplanes and boats and all that, we typically know the speed or the velocity, and we also, which is the magnitude, and we also know the direction it's going. So that's why we can pretty quickly find this component vector. So all we're going to do is say, okay, I want to create this component vector. I know my magnitude is 6, so it's 6 cosine 115 degrees, because that's the directional angle, and then 6 sine 115 degrees. You make sure your calculator is in degree mode. It's probably in radian mode, so switch it over. Calculate this pretty quickly. And I love it that they have a picture over here on the left-hand side to show you what that vector looks like in general. So with that 115 degree directional angle, and you've got yourself a vector that has a magnitude of 6. And that could be 6 feet per second, 6 feet per second squared if you're talking about acceleration. And when you calculate this, make sure you can do this in your calculator. So you should end up with negative 2.536 and 5.438. Notice again the directional angle comes from that positive x-axis. And what else can we talk about with this? That's about it. So if you think about like just graphing this, you'd end up with going negative 2.536 that way. You'd go up, and let me change the colors a little bit on this, and then go up that 5.438. That's a horrible color. And so notice that those movements would create that vector with the magnitude of 6 and a directional angle of 115 degrees. So it all works together. So that's one thing I can't stress enough. It all kind of works together as we move forward. Okay, so let's go on to the back page and get a little bit more into the application. It says find the magnitude. So now we have the component vectors. A and B are both component vectors. We want to find the magnitude and the direction angle of each vector. Now the important thing is, and I'm going to let you do A by yourself, but I'm going to demonstrate the harder one, which is negative 3, or this vector V of negative 3, negative 4. Now, you cannot get away with not graphing it. You need to graph it. Okay, so I'm going to do a quick sketch, and I know that I'm going 1, 2, 3 there, 1, 2, 3, 4 there. Okay, so here's my vector. Now I need to find my magnitude, which is using Pythagorean theorem, so use Pythagorean theorem to find that. And the direction angle, you're going to use tangent. And if you want to get fancy, inverse tangent, because you know to find an angle you need to do the inverse. So let's start with creating a right triangle. Now again, the right triangle needs to be connected or brought up to the x-axis. Now we know we have this movement, which is negative 3. We have this vertical movement of negative 4, and we could use Pythagorean theorem now to find that magnitude. So, and I have no doubt you know how to do this. Negative 4 squared, plus negative 3 squared is going to equal my magnitude of, actually, you know what, I shouldn't try to skip here. We'll end up giving you, I don't know how to, we usually just kind of do it, right? Equals c squared. I'll just do that just to keep it consistent. And once you find this, you'll find that it's 5, obviously. So the magnitude of v is equal to 5. So just use Pythagorean theorem to find the magnitude. And of course, magnitude, the hypotenuse will always be positive, because of course when you're squaring things, they go positive anyway. Okay, so now more importantly, the thing we haven't really done, or I haven't demonstrated, is how to find that directional angle. And this is where I'm going to first, I'm going to switch to a different color. I want to find this angle theta right in here. I'm going to just use a dot to represent it because I can't really get a theta in there. So I'm going to find that angle. So I'm going to say tangent of that angle theta is equal to the opposite side, which is -4, and the adjacent side, which is -3. When you do your inverse tan for 3, you will get your angle theta equaling 53.130 degrees. Now, that is the blue angle. That's this angle right there. That is not the direction angle. The direction angle is the whole rotation, I'm going to do it in purple, from the x-axis, you're going 90 degrees, 180 degrees now, all the way to that vector, that green vector. So you need to take 180 degrees plus that angle you just found, which I like to call the reference I like to call it a reference angle, because it's not the direction angle. Sometimes it is, depending on which quadrant you're in, which is why it says be careful which quadrant you're in here. But really, you have to come up with a direction angle depending on where you're at. So in this case, the direction angle, the dA, is going to equal 233.13 degrees. And I've got to say, this seems maybe okay, simple for you, but this is the part that confuses people. So I just want to let you know, you're always starting at the positive x-axis, counterclockwise, just like the unit circle, to your vectors. So when you find your reference angle, which in this case is 53 degrees, don't assume that's your answer. You need to look at it and decide it. Do you have to add 180 degrees? Do you have to subtract from 270? It's all sorts of different things depending on what your picture is telling you. Okay, so again, you're doing letter A now, and you're going to demonstrate that and show that to me in class. Make sure I see a picture. So I need to see a picture. I need to see how you calculated your magnitude of u, and don't forget that notation, and then I want you to give me the direction angle. Okay, so now we need to talk about bearings, because a lot of times in these kind of problems, pilots don't say, hey, the direction angle is blah. They're going to say bearings. And bearings, as it says up here, pilots often use the term bearing to describe their direction. Bearing is the angle that the line of travel makes with due north, and is measured clockwise. So it's hugely different than direction angle. So to give you an idea, I'm going to do it right here. This is true north, right? The bearing, this right here, is always starting at north and rotating clockwise. So I always kind of joke that in the real world, clockwise makes more sense than counterclockwise, and bearing starting at true north makes a lot more sense than starting on an x-axis. So bearing is starting north, going clockwise. Unlike direction angle, I'm going to just remind you so you see the difference. The directional angle, though, starts here and goes counterclockwise to that location. So you have to really be aware of which one they're talking about. And in example 9, it's a classic, like, here you go. Let's kind of show how it goes here. Example number 9, it says, if David is flying an airplane at a bearing of 50 degrees at 600 miles per hour, so that's what David's flying, it says find the component vector, we're finding this, from the velocity of his airplane. So it says hint, draw a picture, of course, and determine the direction angle. So the bearing, that's where we need to first start, okay? So we're talking about true north. That bearing is 50 degrees off of that true north, going clockwise, not counterclockwise. So we're going this way, 50 degrees. And so he is, and I'm going to change colors just so you can kind of see it a little bit better. So he is right doing this kind of vector right here. So this is 50 degrees in here, that's his bearing. So we need the direction angle. So when we use the math, though, like the formula, you need the direction angle. And in this case, the direction angle is 40 degrees because that's what's in here. And direction angle always comes from the x-axis counterclockwise. So this is the direction angle, and this over here is the bearing. Let me switch back to This is the bearing. Hugely different things. Now, why is the directional angle important? Well, because when we do the component vector, we know the formula is magnitude, which in this case is 600 miles per hour, cosine of not the bearing, and of course people want to put the bearing in, not the bearing. You have to put the directional angle in, which is 40 degrees, and 600 sine of 40 degrees. And I will tell you that's really where I'm going to notice if people didn't watch the video, because people are going to do that wrong. So this here, the 40 degrees is coming from the direction angle, not the bearing. And of course we found the directional angle by finding the bearing. So calculate this out. So his component vector is 459.627 and 385.673. Now we haven't talked, obviously we know that this is the horizontal and the vertical. I've been saying kind of movements, but really I just want to say what that ends up becoming is the horizontal, in this case velocity, and the vertical velocity. So when David is flying 600 miles per hour at 50-degree bearing, what's happening is he is going at a horizontal velocity of 459.627 and a vertical velocity of 385.673, a combined velocity that gives you that magnitude of 600 miles per hour. So just kind of bringing that up, connecting it to what we're going to be doing here in the near future. Okay, so now here's the thing. It says example 10, when David from example 9 is ready to land, he can't find his destination. His co-pilot Amanda points out that he forgot to consider the wind. Yeah, the wind is a kind of a big deal. And in this case, it's going 45 miles per hour due east. Okay, so if you sail, which I'm a sailor, or if you're in the air, and I'm sure many of you have been in a plane where if the wind is against you, especially a headwind, you're actually going to not get to your destination as fast as you may think, or vice versa. If you have a tailwind, that's when all of a sudden the pilot gets on and says, hey, just want to let you know that we're making great time because of our tailwind, and we might, be actually early for a change. So we do need to kind of consider the fact that there are always more forces on us than just perhaps just the one. So let me just, up down here it says, find the component form of the velocity of the airplane relative to the ground, including the influence of the wind. Now, what we do with this, and I don't have a lot of space here, but what I like to do is I go, okay, you know what? I'm going to say the airplane's component vector is 459, because we've already calculated that, 0.627, and the other part is 385.673. Now that was doing great as long as, and then all of a sudden, like Amanda pointed out, he needed to take into consideration the wind. So we need to add the wind vector to this. Now remember, I'm going to kind of scroll down, or up, I don't know how you want to. Remember the other note guide we had where we were just adding vectors right here, where I was saying, hey, you know what, when you have a couple forces on you, you can add your forces, add your vectors together, and as long as you're putting them head to tail. And so that is really what we are doing. Now we could graph this, and don't get me wrong, the graph is kind of cool, but it does take a little while to do. So what I'm going to say is, hey, you know what? Let's just calculate that wind vector, component vector, so we can add those two forces together. So not only the airplane's velocity, but also the wind's velocity. And I'm going to first actually find or talk to you a little bit about this because I don't have the space down in that A area. We know that the component vector of the wind is going to be 45 because that's your magnitude, and we know it's cosine of the direction angle. Now here's the thing, we are due east. If I create an XY axis, we know due east is this right here. This is due east, we're going east. Now what is the directional angle with a vector in that position? How are you rotating off of the x-axis, positive x-axis? And the answer is you're not. So it is 0 degrees. So we have a direction angle of 0 degrees because it is going east. By the way, if this wind was going west, your direction angle would be 180 degrees. If your wind was north, your direction angle would be 90 degrees, and south would be 270 degrees. So again, you have to get your head around those direction angles. So then we're going to, and I'm going to switch over back to my purple, 45 sine of 0 degrees. So that is my wind vector. So I'm going to calculate that really quick for 45 cosine 0. You'll realize very quickly it's 45. 45 sine 0 is going to be 0, and if you think about that logically, it makes absolute sense. You add these two together, and you end up with a vector of 504. So this is the resultant vector, the combined vectors, I should say, and 385.673. So notice that what's happening is we're adding 45 miles per hour just to the horizontal velocity, which totally makes sense because if the wind is going east, that's going to affect your horizontal velocity. Okay, so in letter B, this is like the $1,000,000 question right here. It says find the actual ground speed and direction of the plane. So we want to know now how fast is this plane going with the whole wind and everything, and what direction is the plane going, because obviously it's being affected by that wind. So what we do is we graph, just again, this is for speed, I only graph the resultant vector in standard form. So I actually go out 504, up 385. Keep in mind this is just a picture for our reference. And again, there's my vector. So we always bring it down to the x-axis, and this is 504.627. This is 385.673. And now to find the actual ground speed, we want to find the magnitude. So we are going to find the magnitude of this vector. And so use your Pythagorean theorem to find that. So use Pythagorean theorem to find magnitude. Or I'll even say ground speed, because that's the magnitude. And then to find a direction, you use your tangent. And since the Pythagorean theorem, obviously we're all good with, I hope you can do that in your calculator pretty quickly, you'd find that your ground speed is 635.132 miles per hour at a directional angle, and this is where you use your Pythagorean theorem, not your Pythagorean theorem, I'm sorry, your tangent. So tan of this angle right here, which we'll call theta, equals the opposite over the adjacent, and then you can calculate that. And of course I don't have the space there, but when you find it, you will find that you have a direction angle of 37.390 degrees. So to find ground speed, Pythagorean theorem, to find the direction, tangent. Okay, so if you look at this homework here, this is again 6.1, section 6.1. We've already done these, so we don't need to worry about those, but you're doing 30, 32 through 34 all, 40 through 46, just the evens. Don't worry about 47, and then do 59. Okay, so we will answer any questions you have in class, and also I will check your note guide to make sure that you are understanding it. Take care. Thank you for tuning in.